First, we may need to study on the corresponding cube. We need to know how many vertices does it have, how many faces, how many edges. For a cube, it contains 6 faces, which is simpler for analysis for hexahedron. This hexahedron must be contain 6 faces. Then how many edges are there? We will realize its upper surface and the bottom surface contains 4 edges respectively. In the middle, the enclosed height contains 4 edges. Therefore, it has 12. It contains how many vertices? It contains exactly 4 upper and 4 lower, 8 vertices. On top of such structure analysis foundation, we can find all the permutation group. We realize fixed permutation is the simplest. Such a fixed permutation corresponding image are all remained unchanged. How many different coloring image does it have? Just now we have analyzed that each face corresponding to the permutation solution number. Therefore, in total, it contains how many 6 factorial images. Then, inside corresponding to the fixed point for us, identity elements in corresponding to all 6 factorial, these are all 1 order cycle. Then it contains how many fixed images? Naturally, it is 6 factorial number of fixed images. On the other side, we can enable it to perform rotation. For example, the center of the top face and the center of the bottom face could be connected to form an axis, and this time allow them to perform rotation or positive or negative 90 degree. Naturally, it will produce different permutations. Then in total, how many these kind of permutations? First, we need to know how many axes which are center of faces. Just now, we have said that total of 6 faces. Then how many opposite faces are there? Each 2-face structure an exact opposing face situation. Therefore, it contains 3 in total. There are 3 face center to face center of axes. And we have also mentioned that positive 90 degree and negative 90 degree. Therefore, there are a total of 6 this kind of permutations. Under such a permutation, it is possible to produce some fixed point. We first mentioned that the requirement of this question, all the faces must be colored with different colors. What does it mean? Rotate 90 degree, original red colored face may be changed to blue color. Original blue color may be changed to red. No matter how it is, because it requires each face is colored with different color, as long as you have rotated, it will contain changes. Therefore, it contains no fixed point. It also means that actually we do not need to take out all the coloring images, just need to analyze if it contains fixed point or not. Similar to this, except the positive 90 degree, we can still rotate 180 degree, rotate 180 degree corresponding to face center. Then, therefore, it contains total 3 different axes. Similar analyze them. If we request that each face is colored with different colors, then at last, after rotating with 180 degree, it may contain color changes. Therefore, it does not contain fixed point. Then, is there any other permutation? We will imagine that it was a cube. Could we take this kind of edge and its opposite edge, connecting their center point, structure center of edge and to the center of each edge of symmetry lines, and this time, as long as we follow the symmetry axis to perform flipping, it can still turn back to its original position by following this kind of permutation. How many in total? Edge center to edge center lines are there? Just now we have analyzed how many edges does it contains. It contains 4 top and 4 bottom, 4 vertical, and therefore totally 12 edges. Each opposite 2 edges are corresponding to each other. Hence, 12 divided by 2, it should be 6 corresponding to different edges. Then through similar analysis, after flipping over, the top and the bottom are exchanged. Original red is on top. After flipping, the top will be blue. Therefore, it is still not possible to generate fixed image. Then we do not need to consider it in Burnside lemma. We can also directly take the top vertex aiming to the vertex to the other side to form an inner diagonal line. How are we going to make it flip? We are not going to rotate 180 degree. We are following the inner diagonal line and rotate it with 120 degree. It can be a positive 120 degree and a negative degrees. It can be still coincide. How many this kind of permutation should it be? First, we need to think that how many this kind of corresponding inner diagonal lines. How many vertices do we have? Total of 8 vertices. 2 of them are a pair of corresponding vertices, which may contain 4 different diagonal lines. How many angles are there? Positive and negative 180 degree, 2 angles. Therefore, corresponding this kind of permutation permutation, vertex to vertex, should contain 2 multiplied by 4 different permutations. Up to this point, actually, we did not list the 6 factorial number of all corresponding images. What do we have analyzed? We have analyzed the total of how many different permutations. And at the same time, we have also analyzed that if there are any fixed points generated. It is very lucky that we are requiring each face is colored with different colors. Once rotation is performed, it will change the image. Therefore, it will not have a fixed point, except the identity element. The number of identity elements is very easy to be calculated, which is exactly 6 factorial corresponding to 1 order cycle. It can be substituted into Burnside lemma. We will realize that we have all the numbers, and this time corresponding number of 1 order cycle is 6 factorial, where the corresponding permutations, we may add up all the numbers together. It is exactly 24 permutations. Then how many equivalents are there? Which is 6 factorial divided by 24. The answer is 30. Just now, we have actually used the Burnside lemma to solve the combination of permutation on the blackboard. But does it everyone still remember? We have once asked that, what if we slightly modify the question? Actually, we are asking each face to be colored differently. If so, it would be very easy to find that corresponding rotation does not contain fixed point. But if different faces could be colored with the same color, the size of problem is getting bigger. For these 6 different grids, each grid contains different possibilities. Therefore, the number of all the image set is 6 to the power of 6. And the fixed point could exist with the rotation permutation. For example, if the top and the bottom faces are having the same color, the surrounding 4 faces are the same color. If we perform the face center to the face center's rotation, 90 degree or 180 degree or 270 degree, this image does not contain any change. Which also means that in this rotation, there will be fixed point. If analyzed corresponding image set and corresponding fixed point, the situation is too complicated. It seems that we have met an unsolvable problem for Burnside lemma. Since the Burnside lemma requires us to list out all the coloring image set, the size of color image set could be really huge. Therefore, if we are using just 2 colors, the result might be simpler. If we are using 6 types, 8 types, 10 types, then the coloring image will be very complicated. Theoretically, we may use Burnside lemma to solve it. But in reality, how are we going to find the corresponding 1 order cycles? It is very, very difficult. Therefore, maybe we can change the way we think. Do not start from the coloring image set. Then, is it possible we can use some other paths? In the following section, we are going to talk about Pauli accounting theorem.